Oh, hi. Sorry. Got a little bit taken aback that somebody would try to impersonate me on the chat. So I was hoping to close it and hoping it would blow over. So anyways, I just looked at the calendar and it's like, oh my God, this is my 18th month of working remotely and being kind of free to live wherever I want. And I thought, what a great way to start it live, I guess. Some highlights of my little vacation. I started in Seattle, obviously. It was in for a shock because I had gone to my favorite coffee shop where I used to hang out for most of the day. I was living out of my car at the time. And we had learned that we needed to practice this new concept called social distancing. And then the following day, the coffee shop closed altogether. It moved so fast. And I went to look for an Airbnb. I moved into the Airbnb. And then I turned on the TV, and everybody was talking about this new disease. And markets were crashing. I had some cash because I had just gotten my year-end bonus at work. So I had some cash laying around. I wanted to take advantage of the market. And I so badly wanted to buy platinum. It had dropped to 500 something. I so badly wanted to buy some platinum, but the dealers thought I was crazy. They told me it was going to be years before they ever see platinum again. And I asked, well, do you have silver at least? The dealer said we only had 1,000-ounce silver bars. He couldn't believe I wanted to buy 1,000 ounces of silver because I look and sound very young for my age. And he says, yeah, but it's only 1,000-ounce bars. I went, oh, that's okay. And it took him by a little bit of surprise. And the following day, the dealer had to verify my information. And so I had to dig out my old tax returns and mail and all that. It was a good chance to clean up my car. I just moved into this Airbnb and I dug out all that information. I sent it to him, and I was so relieved that the bar was coming. And then I settled into my Airbnb and I started writing an AI for the game of backgammon. And then the pandemic was going to go longer than anybody had expected. And I wanted to renew my lease at that place. I had only booked it for like a few weeks. And the owner didn't want to extend it. My guess is that she had family who wanted to come home. And I did some research on what to do, and I discovered that there was an eviction moratorium, and she had to extend the lease on the place. So I ended up staying 3.5 months at the same rate that I got, which was like a very discount rate because nobody was traveling. And then I moved on to South Lake Tahoe. I spent about a week there. And it was on the way back that I learned about the George Floyd protest. And on my way back, that's all I heard about on the radio, that there was this protest in Seattle. So the following day after I had arrived back in Seattle, I went to the Chaz area, Capitol Hill Autonomous Zone, and had a great time. You got to remember, I used to have a big fear of loud environmental noises like that. And that gave me a great chance to practice a little bit. June 13th is also a big anniversary for me. June 13th was the day that I went to the Chaz protest. That's a big anniversary for me because on June 13th, 2010, I went on my first solo sexual date after breaking up with my girlfriend. So I was back in Seattle for a couple weeks, and then I headed out again to the mountains. I started with Ellensburg, Washington, where I spent a month there. I used to love to go to Vantage, which is just next door of Ellensburg, to go stargazing, and I always wanted to live there, and I finally got my wish. It was a flop, though. It's nice to go there to stargaze, not so nice to live there. Nothing to see. There's no you know your neighbor kind of vibe, right? Unlike Wallace, Idaho. Phoenix is kind of in between, right? You do know a few neighbors here. Could be better, right? over in Wallace, Idaho, oh my God, everybody knows everybody, right? You definitely you don't want to break up with a girlfriend over there. It'll never go away, right? Now, after Ellensburg, I spent some time in Helena, Montana. On my way into Helena, June 25th, 2020, everybody was supposed to record themselves for 24 hours and upload it, and they made a movie out of it. I recorded myself during the travel to Helena, Montana. I'm trying to remember where exactly I went. I was a little bit unsure if I would get this apartment when I got to Helena. That's why that trip has been a blur, because it was a very nervous time for me. You got to remember, June of 2020, people were still dying left, right, and center, and I wasn't sure if I was going to get into this apartment when I got to Helena. So a little bit of a gamble that I took, and it worked. And I got to meet this very nice owner, and then I spent a month in Missoula after that, where I went walking along the trails. You guys saw me. It was September of 2020. I missed my chance to do. I don't think I want to go there after they start getting cold. Then I went back to Seattle because we returned to the office for a little bit. I spent Halloween in Seattle. You guys saw me. And then I headed out to Wallace, Idaho, and where I really, really found myself. I hope I can get another monthly deal like that for the apartments there. It might be harder this year now that more people are doing what I did. See, had I known this would have gone on for so long, I could have signed a 1-year lease over in Wallace, Idaho, and not have to worry about this. But who knew how long the pandemic was going to go on for, right? So I spent 2.5 months in Wallace, and then I moved to Missoula I kind of bounced back and forth between Wallace and Missoula because I found a bunch of these good deals, but that's okay. I love both of those towns. And then I had a client that I really, really loved working with in person, so I went back to Seattle for a couple months to take care of that. And I felt really judged when I was in Seattle. People don't accept singles for who they are over in Seattle, but I really love my clients that I lived with it. This goes to show how much I love some of my clients. And then he took summer vacation, and now all my clients are remote. So that's when I headed back out to the mountains again. I spent a week in Ponderay, Idaho, and went back to Ellensburg for a month, and then back here to Phoenix, where I am now. Some highlights of, I think when I think back at the pandemic, some highlights that I can point to are in Wallace when I was going on the Christmas festival with this sleigh ride with this truck, going stargazing in Ellensburg, especially the conjunction of Jupiter and Saturn, going on my pilgrimages in Missoula where I took long distance walks along the trails. I would say those are my main highlights, not to mention, of course, not this current girlfriend that I'm seeing, but the previous one. Her mom really wanted us to be together, and I had a very, very nice heart-to-heart conversation with her mom. It was the first time I seriously talked to a future mother-in-law. Very, very good memories. Going out on Valentine's Day as a solo sexual, right? I went bowling, and I held up a sign saying "Single Lives Matter." What else did I do this year? Standing up for myself. I'm really going to have to stand up for myself this next week because at my workplace, we're having a little bit of drama with a requirement to take this drug that Big Pharma is pushing, right? I hate to name what drug it is because this can happen with all sorts of drugs. Maybe next they'll worry that you might go shoot up the workplace, so everybody's got to take antipsychotics to go to work. I wouldn't be surprised if discussions like that are floating around, right? It's a dangerous precedence, right? And so I begin month 18 of my COVIDcation. I want to get out of the Phoenix area, though. I had some drama with this current place that I'm living. I can't receive any mail, and it's giving me a headache with a credit card that expired. And also, my roommates are just poison. I mean, it's not that they're bad or anything, but we just don't have good chemistry. Um, and plus, you don't get this know your neighbor kind of vibe, right? I talked about in the last video about musing about going back to Taiwan. Taipei is a big city, but people still get to know each other much better so than here in the States. Uh, anyway, I'll have to think about that in the coming weeks. Already, I'm getting pressure from work to take this pharmaceutical drug. So, will you stream in Taiwan? Definitely. Uh, it might even work better because when I sleep at night, you guys can watch during the day. So that might even work better. I hope the guy who's impersonating me isn't going to come back here.
Thank you for calling Sanofi Pasteur. If you have a medical information question, please press 1. For all other inquiries, please call back Monday through Friday, 8:30 a.m. to 6 p.m. Eastern Time. Please visit Sanofi Pasteur online at www.vaccineshop.com.
All right. Yeah.
A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians. Welcome back to another video. Have you checked out Linux Wood already? My woodworking channel, posting regularly over there. Link in the description. I would highly appreciate it if you could support the channel a bit by giving a bit of view time to it by watching my first bigger projects that I posted over there. Also, you can see the design process of the products that I sell on stemmerch.eu there, for example. So definitely make sure to check it out. So a while back, I posted this video about integrals with huge conversion problems. And what a terrible video. I really didn't like it, but never mind, it's out there and a lot of people have seen it. So you can be satisfied with everything you post on YouTube all the time. And there was this one integral, namely the one of the cosine, blah 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 of x up until infinity integrated with respect to x. Now, what we did is we said, okay, if we take a look at this integrand right here, we are going to do a little substitution. Namely, you are going to notice if y is equal to the cosine of the cosine blah 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 of x. And what we got here on the inside, since we got infinitely many nested cosines, this is just y yet again. Meaning, I substitute y. And then we are going to get that y is equal to the cosine of y. Now, I said in this video that this fact is pretty surprising, that there does exist a constant which satisfies this fixed point equation. And this is unusual in the sense because the cosine of y, in normal case, if you take a look at its Taylor series expansion, we are going to get that this is 1, and then we are going to get minus y squared over 2 factorial plus blah, 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 higher powers. And if you compare these two, you are going to notice there is no y in here. There is a y missing, but we get a y on this side. And it's pretty surprising, at least in my opinion, that this fixed point equation does have a solution. And the solution to this equation is called Dotti's number, which we are going to basically calculate today, you could say. We are going to find out a closed expression to calculate numerically. You can do it in any other way possible, Dotti's number. And for this, we are going to take a look at this equation, cosine of x being equal to x. And to solve this equation, which is not trivial, not evenly split, we are going to make use of the Lagrange inversion theorem. Link down there in the description for an introduction. This is what it says. And don't be scared, it's not so scary. Okay, so we are going to define ourselves a function f. And we want this function to be analytic. Analytic means, on the one hand, infinitely often differentiable, but this is not the only condition that needs to hold. F being analytic means we need to be able to expand it into a formal power series. If this holds at a certain x naught element of the complex numbers, and if our derivative of our function f evaluated at the point x naught is not equal to 0, then the inverse of our function f is given by this huge expression. I said in the video that you can derive this from the residue theorem. I didn't derive it in the video, it's a mouthful, okay? But you can probably check out some complex anal literature to find out the derivation of this thing. It's not too hard, actually. Now we are going to make use of this abomination of a theorem to get our job done, to find out what Dotti's number actually is. And for this job to be done, what we need at first, if we go through this definition, is we need some function f. And we need to see if it's analytic at some x naught element of the complex numbers. Let us define a certain function f of x at first. Now, we're going to deal with this equation. And what we're going to do now is we're going to subtract x on both sides. It really doesn't matter if you subtract x on both sides or the cosine of x. It really doesn't matter. For simplification purposes, we are going to bring x to the other side, leaving us with cosine of x minus x is equal to 0 on the one hand. But what we are going to do is we are going to define our function f of x to be the difference of the cosine of x and x. Now we are going to define this to be f of x. And what we want to do is we want to get ourselves the inverse function f inverse at the point 0, and this is going to give us the x value, which is going to solve this equation. This is everything that's behind Lagrange inversion theorem, and it's extremely powerful. So now, we defined ourselves the function f of x. Next thing that we need to do is, we need to see if this function is analytical, and we are really lucky. Now, analytic functions, just imagine it to be a Taylor series expansion. If we take a look at this polynomial right here, polynomials are their own Taylor series expansion. The 0 coefficient is just going to vanish in the definition of the formal power series, and everything up to the first coefficient is also going to be just equal to 0, meaning x is its own power series expansion. Now, cosine of x, we know that we can expand this into a power series expansion. The best thing is, since it's defined as being the real part of the complex exponential function, we also know that it's analytic everywhere. It has an infinite radius of convergence. I showed this in another video, link down there in the description. So we got the difference of an analytic function and an analytic function. As mentioned before, imagine it like being Taylor series extensions. This is a Taylor series minus another Taylor series. The difference of two analytic functions is also analytic. And the best thing is, this also has an infinite radius of convergence. Now this is good. So we found ourselves an analytic function. And the best thing is, it's analytic at each and every x naught. It's analytic everywhere. It has an infinite radius of conditions. You can very easily show this. Okay, so it really doesn't matter what our x naught right now is. No matter what it is, it's going to be analytic. So we are going to leave the x naught for later. Okay, we are going to see where we are going to evaluate our inverse function at a later point in time. Now, we need to see if our function, the derivative of it at x naught, is not equal to 0. For this, what we are going to do is we are just going to differentiate it. The inverse function, okay, not the inverse function, the derivative of f is going to be cosine of x is going to turn into negative the sine of x. And x differentiated is 1, so negative 1. So we don't want this to be equal to 0 for some x naught being plugged into here. So we need to restrain our x naught a tiny little bit, because for certain values of x naught, it could also happen that the derivative is equal to 0. For which x naught? Well, obviously, when sine of x naught turns into negative 1. This always happens when we have something of the form, let's go through sine of x, this 1 at power over 2, 3 power over 2, and then 5, 7 power over 2, and so on. We don't want the sine of x naught to get values of this kind, this x naught. That's not something that we want. So by choosing x naught later, we need to be careful when it comes to the derivative evaluated at this certain spot. Okay, that's hard, that's good. But if we choose any old value for x naught, where this condition holds, for example, power over 2, then we are pretty good to go. Then we don't run in any kind of problems. And now, if this holds, we are good to go. We can evaluate our inverse function at, and this time 0, because this right here is going to solve our equation such that we can get our Lotte's number out. This is what it's called. Meaning, if all of the conditions hold, then the inverse function evaluate at 0 is called Lotte's number. Lotte's number in normal case will be denoted with a small r. Very creative. It's going to be equal to, okay, taking a look at Laplace inversion theorem, we are going to get x naught at first and then plus the infinite series where n is greater or equal to 1 of the limit as x approaches our x naught of the derivative in x, the n minus 1's derivative of. And now what we are going to get, in parentheses here, something to the nth power, but what is something? X minus x naught divided by f of x minus f evaluated at x naught. Let's plug all of the information in that we got right here. So in the numerator, x minus x naught divided by our f of x is the cosine x minus x, and negative f of x naught is going to give us what we got right here, just with the signs turned around and x naught plugged in. Meaning this is going to give us negative cosine of x naught plus x naught. And all of this to the nth power. And all of this will also be multiplied by, and now we need to be careful, because we are going to lay at our inverse function at 0 to get Lotte's number out. So we get 0 minus and then f of x naught. Meaning this is just what we got right here, and then to the nth power. Meaning this is x naught minus the cosine of x naught to the nth power divided by n factorial. I know, this looks rather terrible at the moment. I totally agree with that. But now we can make our lives a bit easier by choosing an appropriate x naught, such that a lot of stuff is going to vanish. And don't forget, x naught shall not be of the form 3 power over 2 and so on. Now, which x naught could do the trick, for example, and which one could make our expression a bit easier? One of the x naughts that we could choose is, for example, one where our cosine of x naught is going to vanish. When is cosine of x equal to 0? Exactly at power over 2, for example. Why not choose x naught to be equal to power over 2? Plug all of the values into here, all of the cosines are going to vanish, and then we're going to end up with a hopefully easier equation overall, meaning if we set x naught to be equal to power over 2, then we are going to get that our inverse function evaluated to 0 is equal to Lotte's number, which is going to be equal to 1, Taylor series extension, and this one is going to be evaluated at power over 2. Now we are going to plug all the power over 2's in. Power over 2 plus, and now we are going to get the infinite series, n greater or equal to 1 of the limit as x approaches, and and now our x naught is power over 2. Then we are going to get the derivative, the n minus 1 in x of, and now we are going to plug everything in. X minus x naught is going to give us x minus power over 2. And here in the denominator, what we are going to get is, okay, cosine of x minus x, cosine of x naught is going to vanish, but we need the power over 2 down here. Meaning, what we are going to get is cosine of x minus x, and then we are going to get plus power over 2. I'm going to get rid of this part right here real quick, just to make seeing a bit easier. Then to the nth power. And now, the cool thing is, this part right here is going to vanish in the process. Then we are going to get power over 2 to the nth power. Meaning what we are going to get down here is power to the nth power divided by 2 to the nth power times n factorial. This right here is our Dotty's number, basically. And it's terrible. Computationally speaking, it's an absolute mess to evaluate Dotty's number in any kind of way. It's definitely not fun. But one cool thing that you can rearrange here is that 2 to the nth power times n factorial is the same as n double factorial. Okay, you can check for yourself that this is the case, making the whole thing a bit easier. One thing that Wikipedia is going to state, which is also a pretty cool fact, is that our integrand, basically, our summands that we got right in the Taylor series extension are of the form sum constant, okay, because it's going to be evaluated at some point, some constant an, which is going to be a sequence, times power to the nth power. Meaning Dotty's number in some way is going to be equal to power of 2 plus the infinite series that we got right here, power to the nth power times some an. Which looks a bit more tame, but if you know what an is, and all of this is going to be pretty terrible overall. But yeah, this is Dotty's number, and Dotty's number is going to converge very, very, very slowly to this value. And on Wolfram Math World and the like, you can find a few cool relationships regarding Dotty's number. For example, this one. Basically combining Dotty's number, the exponential function, also the gamma function, they had at 5 or something, giving you this value, which is pretty cool if you ask me. It's a nice coincidence. It's a so-called almost integer, but yeah, this is just a cool connection between a lot of transcendental things. And yeah, Dotty's number. I'm not certain if this thing right here is irrational or the like. Maybe you can double check once again on Wikipedia. But this is all I want to cover for today. Sometimes in mathematics, it's just not nice what you get out. But at least we can find a closed expression in form of a Taylor series expansion, which is not bad overall. You can do it computationally, even though it converges very slowly. And if you are interested in more mathematics that we did today, Taylor series expansions, derivatives, complex numbers, and the like, then I invite you to try out the content of today's sponsor Brian to a kind of sponsor video here on this channel. But his number, never thought about it, sounds kind of weird. But if you take a look at the mathematics that we did today, it's pretty overwhelming, at least to beginners. So we got these derivatives in here. Papa let me turn it into partial derivatives, which is needed, but really doesn't matter if you are in one dimension. And then we also got limits and Taylor series expansions full of crazy stuff. And to make sense of mathematics like this, it really needs a lot of practice. I had a lot of practice too. I wasn't at the point of solving something like this like 5 years ago. No way I could have solved something like this out of my head, for example. But lucky for us, there are a lot of cool resources out there. And one of the resources that I will present to you today is brilliant.org, a website and also a mobile app. You can learn something new on the go, which is going to provide you with some of the best online learning content out there on the internet. And this is my honest opinion. I'm using Brilliant on a weekly basis. I like to show Brilliant to my students in class to learn something about geometry, just number theory, elementary one, prime factorization. It's a very good source to learn all things STEM, starting from mathematics, physics, over to computer sciences, even philosophy and search engines. So good. And the strongest point about Brilliant are definitely their interactive courses. You can interact with graphics, levels, and the like on their website to really get a hang and the intuition behind abstract concepts like group theory, functional analysis, linear algebra. Whatever you can think of, Print got something up their sleeve for you. And it's this feels like something for you, if you feel like learning something new each and every day, then I definitely invite you to try out Brilliant today by using the link at the top of the description, brilliant.org/flammableness. With it, you're going to get free access to a big portion of Brilliant already, but even more important than that, the first 200 people to actually make use of the link get 20% off an annual pyramid subscription, which is a freaking great deal considering how much content they have available on their website. And they are just adding increasingly better courses each and every month, and I can't believe how they can even improve on their current courses all the time. They are so crazy. They are posting such good content, and you should try it out for yourself too. If you want to support the channel a bit, then definitely make sure to become a Patreon supporter or go over to Flammy's Wood and make me monetize the channel. I want to get my money back for all the tools I bought. Hell, there was a lot of money. But never mind, woodworking is fun. Check it out and support the channel this way. Also, don't forget to check out the stand shop you. You can get handcrafted products over there, like my headphone stand and also the securities that I'm selling. And up until the next video, I wish you guys a flammable day. Please stay safe. Ciao.
We're going to talk about thallium. Lots of exciting things. Murders, a fantastic flame color, nice precipitates, and it's very poisonous. I wasn't in the lab when the experiments were done, and I was quite pleased because thallium poisoning makes your hair fall out. Doesn't worry Neil, but makes me feel very nervous.
You look like you've had some hair fall out anyway.
Well, it's been cut a bit, but even Mendeleev had his hair cut once a year. Here got a nice sample, nearly 50 grams of thallium, and if you heat it up, it does melt at quite a low temperature. Melts to a nice silver color, and Neil managed to pour it out quite nicely. You can see the silver metal. But unlike melting lead or indium, it seems to oxidize quite easily, reacts with the air. Thallium, because it is in group 13, has 3 electrons in its outer shell, and it can either lose 1 electron or 3 electrons when it makes a salt. So you can have thallium-1 or thallium-3. We had a nice bottle of thallium-3 nitrate, and Neil decided to make a solution in water, colorless salt, but when he added the water, much to his surprise, it went brown. Not what he expected. He thought the water might be contaminated. Clean water, same result. Phoned the professor at home. What did he think? I made some suggestions, add some acid. No difference, it always went brown. We think it's some sort of decomposition, but Neil quickly lost patience. So instead, he decided to heat the solid thallium nitrate in test tube. Heavy metal nitrates tend to decompose to nitrogen dioxide and brown gas, and the oxide, and the thallium nitrate didn't disappoint. Big clouds and nitrogen dioxide. Much better results with the thallium-1 salt. Was a bit nervous, might go brown again. It was much better, a nice colorless solution. So he tried reacting that solution with, first of all, a solution of iodide, I minus, and there was beautiful precipitate of yellow thallium iodide. Still one of the most beautiful sights was seeing precipitation of solid. Even Brady got quite excited, made Neil do it a second time just to see it. So finally, Neil tried sodium sulfide, and many metal sulfides are colored. Sodium sulfide makes a colorless solution, added the thallium solution, which was also colorless, and a terrific, almost black precipitate. The black precipitate is thallium sulfide. It may well be a mixture of thallium-3 and thallium-1, but it's a sulfide. Most metal sulfides are black. A few have bright colors. I was hoping for something exciting, but it still looked really nice.
Black's exciting. Cool.
The interesting question, why is thallium called thallium? And it turns out that being in the garden is quite an appropriate place to discuss the name thallium. Discovered by two people almost simultaneously in 1861, before Mendeleev had proposed the periodic table. So nobody was sure where there were missing elements. And there were two rival scientists, Lamy in France and William Crookes in the UK. And Crookes had been studying spectra, the light emitted by high temperature samples of salts. And he saw a green line in the spectrum that he thought nobody had ever seen before. And he declared that he discovered a new element. He was so excited by the color that he chose a Greek name after the Greek word palos, which apparently means the green color of a shoot of a tree just as it bursts into leaf. It's quite strange that anybody should have a word for this, but so this is Palos, after which thallium is named. Unfortunately, Crookes only had some residues which came from processing selenium minerals. Probably, I don't know, some quite horrible gunge from an industrial reactor from Germany. So he didn't really have much material in which to try and isolate this element. But he got a small sample. There was a big exhibition in London when people apparently were exhibiting chemical things in the hope of getting a medal. Crookes displayed his spectral evidence plus some what he thought was a small sample of thallium. And Lamy arrived from France with a large lump of thallium metal. So Lamy got the medal. And Crookes was furious because he wanted his discovery to make him a fellow of the Royal Society.